Hello everyone. In this video we're going to be solving a very nice Diophantine equation. So we have x squared plus y squared is equal to z to the third power. You must know the Pythagorean theorem, right? Where we have x squared plus y squared is equal to z squared. Maybe you heard about Fermat's last theorem. When we add two cubes, we don't get a cube, fourth powers don't give us a fourth power, so on and so forth, right? And it's been proven, as you know, by Andrew Wiles many years ago. The proof is probably over 100 pages long and involves very sophisticated, very high-level mathematics. Anyways, why don't we just go ahead and take those two ideas and combine them? So here we are. We're adding two squares and getting a cube. Is this possible with integers? And I will try to focus on positive integers. So let's go ahead and see how we can solve or approach a problem like this. Now notice that z cubed is on the right hand side. And because z cubed is divisible by z, right? Let's assume that x and y are both divisible by z, okay? So let's go ahead and set x equal to t times z and y equals m times z. Make sense? So x and y are multiples of z, therefore they are divisible by z. Okay? Now we're going to go ahead and plug these in, obviously. tz squared and mz squared added together should give us what? Z cubed. Let's simplify this a little bit. We get t squared z squared m squared z squared equals z cubed. You can obviously factor out a z squared here, which is cool, and that gives us t squared plus m squared, and that's equal to z squared times z. Z cubed can be broken down like that, right? Now let's go ahead and simplify this a little bit. We can divide both sides by z. Of course, we're assuming that z does not equal 0, because if z is 0, x and y are both 0, which is not that interesting, is it? So from here, what are we getting? We're basically getting a really cool equation, z equals t squared plus m squared. What does that mean? It just means that z can be written as a sum of two squares if we choose t and m. But that's not it. We can also find x and y from here because they depend on z, remember? X is equal to tz, so x can be written as t times t squared plus m squared. And since y is equal to m times z, remember that's when we assumed that they're both divisible by z or multiples of z, this gives us m times the quantity t squared plus m squared. And you can definitely verify this by way of substitution, right? So we get this interesting trio. If we pick, and you can treat t and m as parameters, for example, if you set t equals 2 and m equals 1, from here you get t squared plus m squared as 5. And then x is just going to be 2 times that, which is 10, and y is going to be 1 times that, which is 5, and z, of course, is going to be 5, because z is equal to this number, remember? So 10, 5, 5 is actually going to satisfy this, or is it? Let's test it. Our equation was, remember, x squared plus y squared equals z to the third power. Now we have 10 squared and 5 squared, which gives us 100 plus 25, which is equal to 125, and that is equal to 5 to the third power. So it actually worked. Let's go ahead and set another pair of values for t and m. Now let's go ahead and assume that t is equal to 3 and m is equal to 2. Which is going to give us something a little bit more interesting, because here we kind of had some repetition. T squared plus m squared is going to be 9 plus 4, which is 13. And then from here, x is just going to be 3 times 13, which is 39. Y is going to be 2 times 13, which is 26. And z is going to be 13. Have you noticed that x, y, and z are they all have a common factor, which is z in this case, right? So x and y are both divisible by 13. But here's the million-dollar question. Are these all the solutions? What do you think? The answer is no. That's why we do have something called the second method, and I think this is going to be a very, very cool way of approaching this problem. I love it. So here's how it goes. And you're probably not expecting to see something like this. I hope so. We're going to be using complex numbers. How so? Let's go ahead and take a plus bi. And by the way, I have another channel that focuses on complex numbers. It's called a plus bi. Go ahead and check it out. So we're going to go ahead and cube this. And when you cube this, let me tell you something. You're going to get a bunch of terms from the binomial theorem. But to keep a long story short, when you separate the real parts and the imaginary parts, you should get something like this. And you can definitely check this out by cubing a plus bi. But that's what you should be getting. Now, let's go ahead and do this. Let's find the absolute value on both sides. Because if two complex numbers are equal, then their absolute values are also equal, don't you think? But how do we find the absolute value? Let's go ahead and do that on both sides. Absolute value of this equals absolute value of that. Well, on the left-hand side, we have something cubed. So we can actually take the absolute value of the inside and then put the cube on the outside. Because 3 is an integer, we're allowed to do it. So the absolute value of a plus bi is the square root of a squared plus b squared. And then I just need to cube it. You got to remember that this is a non-negative quantity. And on the right-hand side, we have the real part and the imaginary part. So taking the absolute value by the same definition should be fairly easy. We get a cubed minus 3ab squared squared and 3a squared b minus b cubed squared. We add them up and take the square root of the sum. Beautiful. Now what does this give us? If we square both sides, take a look. We get rid of the square root. So we get a squared plus b squared to the third power. And on the right-hand side, we get a cubed minus 3ab squared to the second power and 3a squared b minus b cubed to the second power. This gives us a solution. How so? Because if you assume that, okay, this is my z, this is my x, and this is my y, we get the original problem. Z cubed equals x squared plus y squared. How nice is that, right? Now let's go ahead and assume that a is 2, b is 1. From here, x is just going to be, if you evaluate it, x will be 2, y will be 11, and z will be 5. And notice that 2 squared plus 11 squared is equal to 4 plus 121, which is 125, and that's equal to 5 cubed. So we basically verified that this is indeed a solution of our problem. Nice, right? And notice that in this case, x, y, z values, they don't have to have a common factor, or x and y don't have to be divisible by z. Thanks to complex numbers, also check out a plus bi if you want to learn more about complex numbers, because this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.